Any major issues with the homework? Straightforward circuit analysis? Okay, cool. Awesome. Questions about Lab 1? How many people started Lab 1? Yay. Cool. Any issues with that? So I posted links on Canvas to the oscilloscope video and function generator video that Izad made a while back. So those should help, but you can always ask questions. All right, well, let's keep going forward. We're going to do some more stuff with representations of numbers and arithmetic operations, and I'm going to have you do some stuff on the board in groups to make sure that we know how to do this. And this is going to tie into your second homework, which is due a week from today, and which I'll open on Canvas in a moment. So let's look at numbers. So we know about weighted positional notation, right? So one thing to keep in mind is whenever we work with numbers in this course, we want to know how big our number is. If we're working with a binary number, how many bits do we have? Because if we write this, right, in binary, that's the number 5. But if I say that we're working with 4-bit binary numbers, then you want to make sure there's 4 bits. Thanks. Thank you. So in 4-bit binary, I would actually write this like that. And if we were doing 8-bit binary, I would actually write it like this. And those leading zeros are important, right? They're important because computers are not very clever. Right? We're very clever as humans. If we say something like this, and I say add these 3 numbers together, we have no problem with that. We understand 2 plus 1 plus 3 is 6, 1 plus 2 is 3, and we just skip this. And here we just do a 4 and we skip those, and we do a 4 and we skip those. What we're doing in our head is we're adding these numbers with extra zeros in the front. In a computer, you got to actually put them there. So when we do things like binary arithmetic, I'll always tell you 8-bit binary arithmetic, 4-bit numbers, things like that. You're going to want to make sure that you have those zeros in the front. And there'll be a case where not having those will actually get the wrong answer, and we'll see that later today. Okay, so questions about converting between binary, decimal, octal, hex. You okay with that for now? Okay, so let me just show you something you already know. So let's just do 5 plus 7. So this is the number 5. This is the number 7. You want to add them together. What do? 1 plus 1 is 2. But 2 in binary is this, right? So 1 plus 1 is actually 0 with a carry of 1. So I write carries up on the top there. So now I'm doing 1 plus 0 plus 1. Well, that's again 2, 1, 0. So it's a 0 with a carry of 1. 1 plus 1 plus 1 is 3, which actually looks like this. So that's a 1 with a carry of 1. 1 plus 0 is 1. And guess what? That turns out to be equal to 12. So that's 5 plus 7. So that's how you do arithmetic in binary. It's exactly the same process as doing arithmetic with decimal numbers. It's just different where you carry. When you get to 2, that's actually an overflow into the next column. Okay, so we got like 20-ish people in here. There's usually enough space for 3 groups on the back and probably 2 groups on the side and 2 or 3 groups up here. So I'm going to say find 2 people to work with. Let's make groups of about 3 people each and find a spot on the board. And I'm going to put up a few practice problems to let you work with these number representation concepts, and we'll make sure that everybody's doing these things correctly. And then we'll go on to something really cool. So find some friends, find a spot on the board. There should be markers around. If you need more markers, let me know and I'll get some. There should be erasers around also. And let me put some problems up here. So the first thing you want to do is convert the decimal number 47 into binary, and let's do 8-bit binary. And so this is this divide by 2, find the remainder, divide by 2, find the remainder kind of thing. Sorry? Yeah, you can use groups of 3 or 2.
Yeah, I'll go with 4.
You want to just take turns?
Yeah, we can just do one problem at a time.
I think that's 20.
Hey, if you got a second, I guess my payment didn't go through, so I have to get you to sign up.
Okay, come back in.
Yeah.
Wait, yeah.
And then,
You were in here before?
Yeah.
Okay.
And then I couldn't open up the Canvas to try to
Yeah.
to kick me out. Is there a way I can maybe
No,
get that?
it'd be a 0 because it's remainder
like
0.
extension
You do
for
0,
that?
you divide by 2, and 0, remainder 0.
No, you're doing it right now.
So that's
Come back now.
It's overloaded, I'll sign the overloading.
You going into?
Yeah, I'm sure anyone.
Wait, wouldn't it be 2?
yeah, it would be 0. Yeah.
Yeah, it'd be 2 up there. Or yeah, 1 up there.
Yeah, when you get back in, turn the homework in.
And then
0 with the remainder. Okay.
Yep.
So
Well, it's
that's
still on Canvas.
Yeah, it's still open. It'll be up there.
Thank you very much.
All right. And once you have your answer, yeah, go ahead and check it by adding up the powers of 2.
This is a check.
I did the whole thing myself.
So that's good. Keep going. Go one more step. You want to get down, so we got 0.
Is that
Right now you got a 1. Divide that by 2.
Oh yeah, you're right.
Yeah.
Oh, it's
And then you're perfect.
There we go.
Right backwards.
All right. Can you check your answer? Okay. So that's perfect procedure. You just stopped a little bit too early. So you have to keep going until you get down to 0 with a remainder of 0.
Oh, yeah, 1. We did not.
looks perfect, makes sense. Okay, cool.
Doing it this way is a lot easier than the way we did it at 120, where you have to like find the highest power first. That was so much more complicated. This is just like, all right, divide by
I
2.
know. I had my
Keep-
friend teach me this because he's actually in, like he works.
Oh yeah.
The one thing octal.
Okay, so everybody got this.
Right, and X is in groups of 4, right?
Yeah.
So I'm assuming like,
Professor?
Yeah.
Octal is in groups of 3, right? And
Octal is groups of 3.
And then hex is 4, right?
X is 4, right. Okay, so, I forgot my leading zeros there. Good. All right, so, so everybody's got that answer. Okay, go ahead and write that as a hexadecimal number.
You just gotta bring it up to 2. Yeah.
16.
So that is.
Yeah, because that's the highest.
oh yeah,
Oh, 2, yeah, right, 2. Yeah, so 2.
8. So this number. Oh.
Yeah,
okay.
it's 0 through F, yeah.
Yeah, okay.
But it's 16 digits technically
Yeah.
because you include 0 as a
0,
digit, yeah.
and then it goes up to E though, right?
It goes to F. Because F is the highest. Because F is 15. Because it was 0 through 9, and that's the 10 like numerical digits. And then A through F.
Okay.
And that's the extra.
And then we count the 0, that's why it stops there.
Yeah. And it confused me too at first. I was like, wait, why is it
I think I
going
only
16
converted like
plus?
1.
Yeah.
So it's like, it's 2 times 16 plus, that's 2? No, this is, oh wait, sorry, this is.
Conversion.
Like I like working with that and you actually like try it out.
Yeah.
Whereas like you just sit there and you don't know if you know it or not.
Yeah. Have you done that yet?
Oh, we're about to start. We're gonna go in after this class.
Okay, I'll just say it's 16 times 2 is 32, and then 32 plus just E, and that's 47. Okay. That's essentially 0. This is doesn't binary start from choose 2 to 1 or 2 to 0? I think it's 0.
Shoot to the 0, which equals 1.
Okay. Yeah, it always starts at 0. Okay. I'll not start from 1. I thought it was from 1. Because everything.
All right, so everybody got 2F, right? So you can find little tables like this or make one for A through F. It's just 10 through 15. And so it's those 6 binary patterns. Okay, so okay, so now you've got a binary representation for 47, right? I would like you to do the following arithmetic. Go ahead and add 47 to itself. But do it in binary.
I can do this next one.
This is 1, 1, that's 2, right?
That'd be a 1 to carry the 1 again.
Oh yeah.
And then that's the same.
Yeah. Alright, let's double check that. That's going to be 64. 64 plus 16 plus 8 plus 4 plus 2. Does that equal 94? Alright, so 64 plus 64 plus 16 gives me 7. It's a 94. Cool.
So this is the E.
2, 4,
Because you have to think of it instead of like, because it's like the 1 1 equals a 2. So you have to think of the 11, just the 1 dropping and the another 1 going up. Yeah.
Oh, okay.
Are we using actual numbers?
First, like, like, wait a minute, this doesn't
Or are we not thinking of it?
Wait, repeat.
So like when we're say like it's going like this, right?
Yeah.
And say you have this, right?
All right, so everybody got the right answer for this. Good. So, here's a conceptual question. Is there some easy relationship between the first number that you had and the new number that you got, 47 and twice 47? Looking at the binary representations, is there some connection between those? Yeah. When you added 47 to itself, it basically just moved everything to the left one spot. Right, so that's something called a left shift. And it turns out in binary, if you just move everything over to the left, you multiply the number by 2. And that's kind of like what we do with decimal numbers. What happens if you take a decimal number, like 13, and you just move it over one position and turn it into 130? You get 10 times the original number. That's because it's base 10. If you're in base 2 and you move everything over one spot, you multiply by 2. If you multiply by 4, that's just moving it over twice, 2 squared. So that'll be really useful in 270 because that's a way we can do multiplication without actually doing a lot of work. We just have to take everything and just shove it over one spot. And if you move things to the right, you divide by 2. Except if it's an odd number, you lose something. But you do integer division by 2 by shifting to the right. Okay, cool. You've totally got this. So let's make this more interesting. And you can stay at the board. I'm going to have you do something in about a minute. Let's talk about negative numbers. So what are negative numbers? They've kind of got a bad name to begin with. They're called negative, right? Not as bad as like complex numbers or imaginary numbers, but negative numbers are kind of a strange thing. And there was a period in history when people did not think about negative numbers, because numbers were used for counting. I have 1 sheep, I have 2 sheep, I have 3 sheep. Nobody ever came up and said, I have -1 sheep. And if it gets together and meets your 1 sheep, they're going to annihilate each other and we'll have no sheep. That's crazy. It makes no sense, okay? It's an abstract concept to talk about -1, -2. In the same way that if you've done imaginary numbers, the square root of -1 doesn't exist. There's nothing you can square that gives you -1. But we just invent this thing, we call it I, and we say I squared is -1. Well, that's what we did with negative numbers. There is no real number that corresponds to -1. But here's how we can think of a negative number. So -5 is the thing that when you add to 5, you get 0. Okay, so we understand what 5 is, 5 apples. We understand addition. -5 is the thing that when you add to 5, you end up with 0. And this requires us to know what 0 is, which is also a weird concept at some point. So -5 is the thing you add to 5 and it gets you to 0. Okay, we would like to define negative numbers in binary. And we're going to use the same kind of trick. So let's think about 4-bit binary. And the number 5 is 0101. So what you want to do is find some 4-bit binary number that when you add to the number 5, you get the number 0. So play around with this for a few minutes. Think about adding different things to this number 5 in binary and see if you can find something that leaves you with 4 zeros. And it's kind of a trial and error.
Could you fold it
thing,
over
sort of.
so it makes it so everything carries over, so this makes it goes to the 5th bit.
And you may not get exactly to 0, but see what you can get that's pretty
I was
close.
thinking we're trying to add it, so because it's in 4 bits, so it's like 0, 1, 0, 1. I'm trying to get it so it goes to whatever number you have, and then you add that together, then you get it to so it carries over. So this the 4 bits here are 0,
Right.
but the bits carried over to the 5th bit. But the 5th bit doesn't exist, so it just resets.
Right.
That's what I'm trying. That's what I'm going towards. Because you have to add it. like subtract the same
So
number.
we'd have to basically add something that has
Well, I
negative
think
numbers.
Yeah, it makes this number go over. So I'm trying to think of a number real quick.
Like,
You could just move the ones.
we'd have to add, what is that? 11 times, yeah.
You have to make Steve Jobs. Because this is.
Oh, I think you're right. Invert.
Yeah, but then it's
Four times minus one or four zeros. Just
Add 1. This is 0, 1, 0, 1, and then
this is
Okay, good.
easy win.
I mean, to get that, you're just gonna right? Because negative that goes negative 1.
Oh, you're down there, okay.
And that's 2 again. That makes it here.
So did we start this as originally 0?
Yeah, we originally invert one. Yeah, what he was saying, yeah. Just invert it and added the 1. So the first digit is here. And then it shifts it over all to the left and makes it so these 4 bits are 0, but technically there's a 50 number. But we don't look, yeah.
All right, so this is great. So it looks like what most people did was something like this. Let's see, usually put it on the bottom. Right, so 1 plus 1 is 0, carry the 1. 1, 0, 1 is 0, carry the 1. 1, 1, 0 is 0, carry the 1. 1, 0, 1 is 0, carry the 1, and then you've got an extra 1 over here. And that's not exactly the same as just zeros, but all we got to do is say, you know, when you do this addition, just keep those 4 bits. Ignore anything that comes out of there, and we've succeeded. We found something which, when we add to 5, gives us 0. And so we're going to say this is negative 5. So you have invented something called 2's complement notation. All right, so you can go ahead and sit down if you like. Let's talk about 2's complement. So 2's complement is a way to represent negative numbers. And there's a trick we can use. So what I saw some people doing was writing down a blank here and then saying, what do I have to add to give me a 0? Well, I got to add a 1. And then I have a carry. And what do I have to add here? I have to have a 1. And that gives me a carry, and I have to add a 1 here, and so, or a 0, and so on. Right? So there's a procedure we can use to write the 2's complement of a number. So it's a 2-step procedure. The first step, so to find the 2's complement of some number n. So the first step is complement or toggle each bit of n. Complement means if it's a 0, replace it with a 1. If it's a 1, replace it with a 0. So if our original number n is 0, 1, 0, 0, 1, 1, 0, 1, I'm going to complement every bit, and I'm going to write down 1, 0, 1, 1, 0, 0, 1, 0. And that's almost the answer I want, but what do I get if I add a number to its complement? Everything's going to come out to be a 1, because if I had a 1, I'm going to add a 0, and if I had a 0, I'm going to add a 1, and I'm not going to get any carries. So that's going to get me a bunch of 1s. And then step 2, I'm just going to add one more. Because if I add 1 to this, now everything is going to be a 0 and it's going to generate a carry. 1 plus 1 is 0 with a carry, 1 plus 1 is 0 with a carry, and so on. And we'll get that last carry out of the last position, which we're going to ignore, and it's going to leave us with 8 zeros in this case. So anytime we want the 2's complement of a number, toggle every bit in the binary number, and then add the number 1. And that'll always get you the 2's complement. So in the 4-bit case, we had the number 50101. Toggle every bit 1010. Add 1 1011. The advantage of doing negative numbers with 2's complement is that because we found this by saying, give me something that when I add to n gives me 0, all of the stuff we know about arithmetic still works. In particular, we can subtract by adding the negative of something. We can do a minus b by doing a plus the 2's complement of b. And that's really useful because we like doing subtraction. So let's look at 4-bit numbers. Do you know how to write numbers in binary in order, by the way? This is something we do somewhat in 120. 4-bit numbers, okay, forget about negatives for a moment. 4-bit numbers, how many different numbers can I represent with 4 bits? Do you know? 16. But the largest number is 15, because we start with 0. So, do you know how to write down the binary numbers 0, 1, 2, 3, 4, 5 all the way up to 15? Okay, so if you don't, or if you need to go up to 5-bit numbers or 8-bit numbers, here's a trick, right? Start off with 0, 1. That's easy, that's just 0, that's just 1. And then if you want to do 2-bit numbers, just repeat what you just wrote, and now add a first bit. For the top half, add a 0, for the bottom half, add a 1. So now I got 0, 1, 2, 3. Now if you want to go 3 bits, repeat what you just wrote. And on the top half, put 0s in the beginning. On the bottom half, put 1s in the beginning. So there's the numbers from 0 through 7. So you can do this for 4 bits. All right, so there's the numbers 0 through 15 if we're not doing anything with negatives. So what does the number -1 look like if we do 2's complement? So now we're going back to dealing with negatives. So here's the number +1. What would -1 look like? How'd you get that?
You flip it and then add a 1 here.
Okay, so if we flip it, we get 1, 1, 1, 0,
Oh,
and then add a 1. We actually get all 1s. So this is -1. You ever look around your computer, like doing internet installations or stuff like that, and you see lots of numbers pop up with a lot of F's in them? Like FFFF, 83, blah, blah, blah. Those F's are successions of 1s, right? This is an F in hex. And when you see a bunch of F's next to each other, you're probably looking at a negative number. And -1 is a really popular negative number in computers. So you see lots of like 8 F's next to each other. It's a 32-bit version of -1. All right, what about -2? So here's the number 2. Complement it. add 1, 1, 1, 1, 0. Hey, that's right down here. So what would you guess this is? Good guess. What's going on with this last number, 1000? We've got all of these numbers, and when we complement them, we get these. What about 0? What's negative 0 look like? There is, though. Negative 0 should just be 0, right? So what if we do the 2's complement of 0? What are we going to get? So write down 0, complement every bit, add 1, you get 0 again. So this is also negative 0. So that's good. That's a warm fuzzy moment. But we got this oddball down here. There's nothing left that we can negate to give us this. We've got 0 through 7. If we negate 0, we get this. If we negate any of these, 1 through 7, we get these, negative 1 through negative 7. What's the deal with this? Well, this turns out to be negative 8. And we cannot write positive 8 in 2's complement, because positive 8 would look like this. So why is this negative 8 instead of positive 8? Because this first digit tells us if we have a negative number. It turns out in 2's complement, anytime this first digit is a 1, we've got a negative number. So this is negative 8, kind of by convention. And this is slightly weird because positive numbers go up to 7, negatives go all the way down to negative 8. So it's like we have an extra negative number. Bless you. All right, so we can think of this as like a sign bit, S-I-G-N. It tells us whether the number is positive or negative. If it's a 1, it's negative. If it's a 0, it's either positive or it could be 0. Yeah?
Wait, so it can't go to like negative 10, 11?
It can't, because with 4 bits, we're limited from positive 7 down to negative 8. If it's an unsigned 4-bit number, it goes all the way from 0 to 15. And in programming, if you're doing programming in, say, C, you can say, do I want this thing to be an integer that's signed or that's unsigned? If it's a signed integer and it's 32 bits, it goes from about 2 billion to negative 2 billion. If it's unsigned, it goes from 4 billion down to 0.
What does sign mean again? Is that the 1 or the 0?
Signed, if we say that the number is a 4-bit signed number, it means it has a plus or minus sign in front, so it's like this. If it's a 4-bit unsigned number, it's just plain old binary. It's just, I didn't write it down, it's just 0 through 15. That comes up more in computer science than it does in digital logic, usually. So this is the way we'll mostly deal with negative numbers in this course. But it's not the only way we can do negatives. And this is not what we do as humans. This is not how we approach negative numbers. As humans, here's the number 5. How do I write the number negative 5? I just throw an extra symbol in front. But if I want to do 7 minus 5, I can't just say 7 plus 5 is 12, and 1 plus dash is, something, right? This breaks our way of doing pencil and paper addition. We have to switch gears, and we have to say, oh, I'm subtracting. 7 minus 5 is 2, and the borrow is 0, and all that stuff, right? With 2's complement, we can just do straight addition, and it's actually doing subtraction for us. With this notion of adding an extra symbol to say it's negative, we have to do extra work. But we can do this in a computer. we can use something called signed magnitude. And signed magnitude says if you have some positive number and you want to make it negative, just change that first bit to a 1. But now if I add these together, I'm definitely not going to get 0. I have to use a different piece of hardware to deal with negative numbers. So usually we do 2's complement, but there's places where you might want to do signed magnitude, in particular when you're interfacing with humans, because that's what we're used to. Logged me out. Bummer. All right, so homework 2 we'll be due in 1 week. And it's basically stuff you've just done. So 3 questions. First question, convert some numbers from decimal to binary. Second question, convert some numbers from binary to hex. And then the third question, I want you to do binary addition like you already did on the board for these 3 situations. So you're going to, in part 1, convert 23, 79, and negative 28 to 8-bit binary using 2's complement. Okay. I should actually say that. So use 2 complements. 2's complement for negatives. All right, so down here in part 3, you're going to do some addition and subtraction. So 23 plus 79, just take your answers for A and B and add them together as binary numbers. 79 minus 28, take your answer for B, take your answer for C, and add them together. Okay, forget about the fact that this one is negative, just do your regular binary addition. And then the third one, do 23 minus 28, take your answers from A and C and add those together. In each case, you're going to end up with a binary number as an answer, right? Make sure it's clear what that number looks like, but then convert your binary number back into decimal. And when you do that, you should get the decimal version of 23 plus 79, 79 minus 28, and so on. So there's one potential subtlety in converting back to decimal when we're dealing with 2's complement. So let's do 4-bit. And if I say convert this number 1011 to decimal, you've got to know, are we doing 2's complement or not? So if we're doing 2's complement and we want to convert this to decimal, we cannot just take the powers of 2 and add them up. So that's going to give us 1 plus 2 is 3 plus 8 is 11. And we know this is negative 5, right? So when you do your conversion to decimal, 1, check the most significant bit. If it's a 0, just add up your powers of 2. Because if that most significant bit is a 0, it's a positive number, there's no funny complementing adding 1 going on. Just add up the weighted powers of 2 and you're done. If the most significant bit is a 1, as it is here, you need to do the following. Take the 2's complement, which will change that most significant bit to a 0, convert to decimal, and then negate your answer. In other words, if I see a 1 here, I know this is negative something. So find the negative of this thing, convert it to 2's complement, that tells me what it's the negative of. So take the 2's complement, change that to decimal, and then throw a negative sign in front. So for example, 1011. So if I want to take the 2's complement, toggle everything, 0100, add 1, gives me 0101. That's equal to 5 decimal, and so my final answer is -5.
Wait, so you added the one in the other one?
So we're trying to find the value of this in decimal. So I looked at this bit here and I said it's a 1, so this is a negative number. So I took the 2's complement, which means toggle each of your bits, 0100, and add 1, 0101. Convert that number to decimal, that gives me a 5, and then throw a minus sign in front. So that tells me that this number is equal to -5.
Would say if like the number was just a 3-bit number and it was just 011, then that would just be a normal 3, right?
If it's the 3-bit, yeah, if we're talking about 3-bit numbers and we have this, that's just equal to 3.
Can't you just take the decimal of the smallest 3 digits
And
then
subtract from 16.
subtract 2?
Oh,
After you,
I don't know if that always works. I thought you were going to say take the decimal of the whole thing, subtract from 16. I don't think 2's magic.
okay.
So let's try this.
So I tried it with -1 in my head and it seemed to work.
So that should be -1. So what's your algorithm? Proposed algorithm?
So basically, oh no, I got it mixed up in my head.
Okay, all right. So if we wanted to convert this into decimal, we'd look at this first bit, we'd see that it's a 1. So we want to take the 2's complement of this. So toggle all the bits, add 1. That's the negative of this, that's the 2's complement. Convert it to decimal, that's a 1, and then throw a minus sign in front. So this is equal to -1. Is that making sense? Yeah.
I was wondering if you added a 1 you did there, wouldn't the last digit be a 0?
If I add a 1,
Because you're adding a 1 and another 1 from the 1111.
so first I complemented this to get a bunch of zeros, and then I added 1 to a bunch of zeros, which gives me that.
Oh, so you're okay.
Right, so you're not adding this and this and this.
Adding that, okay.
Yeah, so change it into that, add a 1. Is that okay? All right, well, you get practice on it on the homework. The homework is due on next Thursday, so that doesn't mean you have 7 days for the homework. You have like 4 or 5 days for the homework, because you want your homework done by Tuesday, so that if you go through the homework and you don't understand, say, how to do this part of it or something, Tuesday in class, when I say, are there any questions on the homework, you can say, yes, none of it makes sense, please explain it again, right? And I'm happy to spend class time on that. If you don't start it till next Wednesday, and you're like, I don't know how to do any of this, right, then there's no chance to come in and talk about this in class. So pretend it's due on Tuesday. You don't have to write it up all nice and neat, but make sure that you can get to the solutions, right? And, you know, this last part in particular, which is the trickiest part, question 3, there's an easy way to check whether you did it right, because when you're done, you're going to end up with binary numbers, and you can convert those back to decimal, and they should be equal to, you know, 101 or 51 or -5. so you can confirm whether you got the answer right before you actually like turn it in, which is the best kind of homework. All right, let's do a 5-minute break, and then I want to talk about truth tables some more, and I want to start working towards doing some circuit design.